with where we had stopped on the first day. We were just discussing generally about it. Now I think we'll not go much in detail. We'll directly go into the types of reactions and all that. So text and PPT will just refer to in between and go on. So I'll start sharing. This is what was the basic learning outcomes from this chapter. Classifying the various organic halo compounds, we had just briefly discussed that day. Then naming the organic halo compounds, trivial names as well as the IUPAC based on the IUPAC system. Then the nature of the CX, the polar bond, CX bond, we'll be able to understand that. Then the general methods of preparation of both haloalkanes and haloarenes, the student will be able to know the preparation methods. He'll be able to explain the physical and chemical properties of haloalkanes and haloarenes. Physical properties, basically the boiling point variation, then melting point in aromatic haloarenes, then coming on to solubility and understand the various reactions of the structures and correlate the structures of haloalkanes and haloarenes with the various properties. Why that particular reaction is happening or not happening is dependent on the structures. Then the mechanism, main aspect here in this chapter is the mechanism of the nucleophilic substitution reactions. Elimination, we are not moving into the mechanism, only for the nucleophilic substitution. Then the stereochemical aspects of nucleophilic substitution reactions. Then distinguishing between the SN1 and SN2 mechanism. And the child, once understanding the complete content, the concept in this chapter, will be able to solve interconversions related to the reactions mentioned here and then connect it as we go on to the other chapters. And the latter part, we have polyhalogen compounds, a brief mention about it, and the environmental effects of polyhalogen compounds. So once we do this chapter, the child will be able to relate to all this and work on it. So basic things, this is all the introduction that we give where we find halogen compounds related to daily life, some examples in medicines and all that. And all this classification we had covered. So main part, preparations we had discussed that day. Now moving on to the reactions, it is nucleophilic substitution reactions, one main type. Then we have the other type of reaction shown are elimination coming on, and then the last type is reaction with metals. So these are the three categories of reactions, and main one is where you're having haloalkanes being substituted by a stronger nucleophile. So based on the reagent used, we can convert haloalkanes to a number of other products. And so in many of the conversions, we can see if we convert it to an haloalkane or haloarene from haloalkane, from there going on to other products is much, much easier. So that way, knowing all the reactions of haloalkanes, haloarenes is very important. It's the basic things here. So where it can be converted to alcohols, it can be converted to ethers. Then halogen exchange, which we discussed the other day, iodo and fluoroalkanes being formed. Then converting haloalkane to amines and all the derivatives of amine, primary, secondary, tertiary, converting into nitrile and isonitrile. So in these two aspects, when we come into this too, is where we have to be a little more careful. Yes, namaste, Prabhakaran sir.
Namaste, ma'am.
Namaste, sir. Yeah.
Namaste, ma'am.
So here we have to stress upon these two reactions about the ambident nucleophiles. Like the other day, Radha ma'am was discussing about ambident in coordination compounds. Here we have the same case coming in the case of ambident nucleophiles reacting. So potassium cyanide and silver cyanide, teachers, how do you explain it to the children? Why the products are different? How do you go about discussing KCN and AgCN? If one of you teachers could just explain KCN and AgCN as ambident nucleophiles and potassium nitrite and silver nitrite acting as ambident nucleophile. What is the reason for that? How do you all explain? Why does KCN give cyanide while AgCN gives isocyanide? So it depends on the Bhanumati ma'am, if you could just elaborate on it, how you explain. So KCN is an ionic compound. Yes, ma'am?
Yes, ma'am.
So it will be dissociating to give K plus and cyanide
Cn
ions, so
minus.
Cn minus. So it can attack through the carbon part in the case, and therefore Rx is being converted to Rx plus Cn minus. So it's attacking through the carbon, and therefore we are getting RCN. Whereas when it comes to AgCN, what is the case?
Cn minus.
Is the bond between silver and carbon is a covalent bond, and
bond.
not ionized there. So as a result, the attack onto the alkyl part will be through, in the case of silver,
Nitrogen. Through nitrogen only.
will be through the
Nitrogen.
the lone pair present on nitrogen. It is the lone pair on nitrogen which is forming a bond with the alkyl part of haloalkane. So that is the reason why you're getting isocyanide here. We are getting isonitrile or isocyanide as the product, because here the AgCN bond, AgC bond is a covalent bond. It will not ionize. You are not going to get components. So it is through the lone pair on nitrogen. And similarly, when it comes to potassium nitrite and silver nitrite, we are getting two different compounds. Potassium nitrite is
K plus NO2 minus.
yes, K plus and NO2 minus, N double bond O. So here the attack is through oxygen, becomes NO2 minus anion, bonding through oxygen to form the, and it's named as alkyl nitrites. The RON double bond O is bonding through this oxygen to the alkyl part, the carbon, forming alkyl nitrite. Whereas silver nitrite, Ag bond is a covalent bond. Ag bond is a covalent bond, so it will not ionize. So in that case, the carbon bonds to the ONO part through the lone pair on nitrogen, and thereby we are getting RNO2 and R bonded to N, the carbon bonded to N in such compounds are named as nitroalkanes. These two specific things, when we teach the children, it's slightly reasoning part and explanation part coming in there. So there we are having formation of nitriles, isonitrile, and this is a very important reaction, is it not? Converting, because in interconversion step, this is a reaction where we go in for ascending of the series. When we talk about the number of carbons in the product, one of the ways is by, suppose it's an alcohol or an acid. Alcohol, you'll convert it to a haloalkane by convert of carbons, and thereby go into other products. So this is a very important reaction. Reacting with sodium or potassium cyanide, haloalkanes, is a very important reaction used in step-up reactions or ascending the series. So that very important when we have to instill on the child. This is very important. We have to use it and all that. Then coming on to the other one is where we are converting it to esters using silver salt of higher fatty acids, of carboxylic acids. Not higher, silver salts of carboxylic acids, we can convert it to esters, and reducing agent, lithium aluminium hydride. So using the reducing agent lithium aluminium hydride, haloalkanes will be reduced to the corresponding alkane, same number of alkanes. So that is one method. Then we can also prepare higher alkanes. How is the possibility? Rx, how can I convert it to RR? So when we are treating with lithium aluminium hydride, if I'm using Rx, or say if it is chloromethane, we are converting it to chloromethane with lithium aluminium hydride gives chloromethane with lithium aluminium hydride. Methane. Chloromethane with sodium and ether. Chloromethane with sodium and ether.
Sodium and that is also ethane.
Chloromethane with sodium and ether will give ethane, right?
Yes,
Ethane.
ma'am. Yes, ma'am.
Chloromethane with lithium aluminum hydride will give methane. Chloromethane with sodium and ether gives double alkyl group. What was that reaction? Name reaction?
Woods reaction. Woods reaction.
Woods reaction. Woods reaction. And
Woods
here
reaction.
we are using alkyl metal, is it not? Metal substituted alkyl compounds will result in higher alkane again. Alkyl lithium compounds. If I use CH3Li, it will react to give a higher alkane. So this way. So we can use a mix. You can get a mix of different alkyl groups. If I start with Rx and treat it with say R-Li, I get RR- as my alkane, a higher alkane. So Woods reaction and Woods reaction specifically, we use it. We don't use it for preparing a mixed alkane or not for preparing alkanes with the odd number of alkyl groups, carbons, is it not? That is one reasoning question we give the children. What is that answer? What do you give for that, teachers? Woods reaction is used or preferred to prepare alkanes with even number of carbons, not for odd number. So to prepare odd number, we will be needing
Lithium aluminum hydride.
lithium aluminum hydride. Going for Woods reaction, what will happen, sir?
Woods reaction, it will give only even number of.
If I go for, if I have to prepare using Woods reaction, I'll have to use
sodium and ether.
I'll have to use two different haloalkanes, right?
This is I think Woods Fittig reaction.
Yeah. No, this is Woods reaction. Woods reaction. But here, what will be the problem if you go in this way? The earlier example which I discussed was where we go for chloromethane with sodium in ether. So we are using 2 moles of chloroethane and 2 sodium, whereby we get ethane. Ethane and sodium chloride. But when we use 2 different haloalkanes, there it was 1 haloalkane. Now we are using 2 different haloalkanes for Woods reaction. In this case, what will be the possibility?
Here also that odd number propane has to form. Propane has to form.
Propane has to form, yes. We can get C3H7, is it not? Sorry, C3H8 here. Then, any other possibility coming in? We can have a combination, self-combination, right? You'll have many molecules. So we can have a self-combination between chloromethane. That will result in ethane. And a self-combination of chloroethane molecules will relate in, you'll get butane, right? Yeah.
Yes.
So there's a possibility of a mixture of alkanes coming in when we are going in for Woods reaction involving different haloalkanes. And the separation of these becomes difficult. Separation of this becomes difficult. And that is the reason why we don't go in for Woods reaction for preparing. Yeah, so we are getting the odd number alkane, but for that we need to use 2 different haloalkanes. Results in a mixture. So that is not a very efficient method. So mostly, but we do go for Woods Fittig reaction for preparing alkyl compounds. So normally, so we don't employ Woods reaction for odd number alkane containing compounds. So we go for self, only 1 mole coming in there. So these are some of the important that come in when we are doing that as that part of it. So this one, so these are the major nucleophilic substitution reactions, and for that we have to go in for the, so we can give the children, when we teach them, we can give a mind map, a map like this, tell them to fill up and all this. So these type of ways by which we can give them a practice of questions. So now we'll move on to this nucleophilic substitution reactions in detail. So the concept of optical activity comes in when we have what type of compounds. So optical activity. So the other day I just started discussing optical activity in coordination compounds also. What type of compounds show optical activity? Can we, looking at the molecule, can we find out if it is optically active? If not, how are we going to find it as optically active? And organic compounds is a very easy method. Yes, ma'am?
Asymmetric carbon should be there.
Yes, we have to look at a asymmetric center in the organic compound. That way we can easily identify whether it's going to be optically active or not. And identifying the optical activity is basically its rotation, plane of polarized light. When we pass it through the sample, the plane of polarized light, if it is in clockwise direction, dextrorotatory. If it rotates it in anti-clockwise direction, then it is levorotatory. So it can only be experimentally found out. The optical activity will be only looking at the molecule, you cannot identify. So only if it is given like say plus, minus, deform, plus, minus and all that, we'll know. Otherwise, no idea. We won't have an idea about it. So finding out how, whether the molecule is, showing optical activity. So the very first, you can introduce it with a lot of examples, isn't it? Optical activity. So in nature, so we talk about enantiomers. What are enantiomers? Stereochemistry, very important aspect. Enantiomers. The first, I think the terms we talk about, we introduce here is asymmetry, chiral carbon and all that. Then coming in stereochemistry, superimposable mirror images, non-superimposable mirror images. Then comes in enantiomers. So we can give a lot of examples where, so chiral molecules, because we can see the mirror images will be superimposable. Whereas the best example that we always give is our palm, is it not? To talk about the non-superimposable mirror image. This is the best example that we can give. And then coming on to the molecule, when it comes in, a carbon, if it is bonded to all 4 different groups, atoms or group of atoms, then that is what, that can show, that will have a non-superimposable mirror image. So identifying the asymmetric carbon, very important. Whenever a compound directly, sometimes you have to find, the child will have to find out which carbon is having all 4 groups different. Even if one asymmetric center is there, that can show optical activity. So this is the basic introduction that we will have to go in there when talking about asymmetric molecule. So, and nowadays, because we have the convenience, so we have our ball stick models and all in our school. So this is the best method. We can have 4 different, is it not, colored balls attached, and based on that we can show the child, make the children understand what is an asymmetric carbon. And now also using all this, we can show them a lot of pictures, a lot of videos by which the child will be able to relate. So an asymmetric carbon with all 4 different centers and the mirror image of it. So the mirror image is non-superimposable. If you try to rotate by 180 degree and try to place that on it, you will see it will not match. So it is not going to superimpose. So such type of compounds will be showing optical activity. So what is an enantiomer? How do you define an enantiomer to your students?
Equal amount.
No, ma'am. Enantiomers.
Stereoisomers,
which are? So these examples, yeah, which are non-superimposable mirror images of each other. So such types. So if you have an asymmetric center, a carbon with 4 different species, you take its mirror image and then try to superimpose on it, it will not be superimposable. So these 2 are called as enantiomers. So the figure that we saw earlier, so these 2 are different species. So they are enantiomers. Now what about enantiomers' properties? Will they differ in their properties? Enantiomers?
They have the different optical activity, ma'am.
Yeah, only that. No, sir. Yes, they differ only in their optical activity. All other properties will be similar.
Same.
Yes, sir. Yes. So all other properties being same, they differ only in their obstro and levorotatory. So that's what, so very important. The child has to understand what is an enantiomer before going into all these aspects, because everything deals here. And coming on to SN2, SN1, though we have cases where we'll have asymmetric molecules and symmetric, this way. So SN2 and SN1. So SN2. So the name, as the name comes in, SN2. So S stands for substitution, N for nucleophilic, and 2 for bimolecular. That's how we introduce to the child. So, and what other things? So from the name, so substitution, nucleophilic, bimolecular coming in. So what does this 2 stand for?
It's
So
a
what does it show?
bimolecular reaction, ma'am.
Yes,
Because the
bimolecular. So when we talk
is
about a reaction, we are talking about reactions of haloalkanes. So we are having Rx here. You're having the substrate because that's the main component here, Rx. And then it's a bimolecular reaction. So it is also dependent upon the nucleophile. The rate of the reaction depends upon both the substrate and the nucleophile. That is why it's a bimolecular reaction. So when we express the rate of reaction, K is equal to, rate is equal to K into concentration of the substrate as well as the nucleophilic acid.
Concentration of the
Yes.
nucleophile. Yes.
That is why, so 1 and 1. So it's a second order reaction. So that's it. So, and what happens? What about the number of steps involved in this reaction? So when we tell the children,
Single
2.
step, ma'am.
Yes, it's a single step.
1 means 2.
Yes. 2, in the name there is 2, but the step will be 1. 2 stands for the rate, how many, both participating. And so what happens during the course of the reaction?
Inversion takes place,
Yes.
ma'am. Walden inversion. Yes, ma'am.
So here we are having a simultaneous attack, is it not? As Rx leaves, X leaves, at the same time you're having the attack of the nucleophile.
Nucleophile.
Yes, and then this breaks off and then nucleophile comes in. So during this course of the reaction, what is happening? What is this that is formed here?
Intermediate.
Do we call it as an intermediate?
No,
Is
ma'am.
it stable?
Transition state.
Unstable.
Transition state.
It's just a transition state. It's not forming this as, because you know here, in this case, you're having how many bonds coming in?
5 bonds.
Actually,
ma'am.
around
5
R, it will be 5.
5 bonds, is it not? So when we look at this, when the nucleophile attacks, you're having 5 bonds coming in. 1, 2, 3, 4, and 5. Highly unstable. So this is not an intermediate. It's just a transition phase. As this moves off, before it breaks, this is coming and attacking. So we cannot say, so that's why we say it's a one-step reaction. As this goes, as the X is leaving, the nucleophile is simultaneously attacking. And thereby you're getting a transition happening and immediately it'll get converted. It is not, you cannot isolate, it doesn't form. So this is it. So this is how you show an SN2 reaction, is it not? So direct one-step reaction, just showing the transition state in between. So bimolecular, 2 comes in from there, N from substitution. So NU is substituting for X. So in the name substitution, and it's a nucleophile. So nucleophile, nucleus-loving species coming in. Now, a very important aspect here in the case of SN2, SN1 differentiation. What is the main aspect coming in? Or I think that discussion will come out later. So basically the step here, and as you were saying, teachers, there is an inversion. When it's optically active, there will be an inversion of configuration, is it not? Because always the attack is from the
opposite side.
Back side. So we can show a lot. I think there are a lot of GIFs, animations, everything coming in where we can show the children nowadays. After now we have started with blending learning, you can show. So you can see as this is brown and green coming and attacking simultaneously. Then I have another one here where you're having OH group coming and reacting. As Cl leaves, this is also binding and then Cl leaves. After this binds only, it is leaving. So you can see the transition state being formed and then this is leaving off. Another picture where you can see the nucleophile coming and attacking, and after that this leaves off. So you have a lot of pictures, different types of GIFs and all that, which you can use so that the child seeing it, they understand much more than just we draw on the board and all that. So this way, a very good way of showing and making the child understand. So that's SN2, and the main thing here is the inversion of configuration. And the best example analogy we can take is the inversion of an umbrella on a very windy day. You try to use the umbrella, no use, it just gets inverted off when during rain. So the same thing happens here. You have X on this side and it's completely getting inverted, and the nucleophile comes onto the other side. So inversion of configuration is the main aspect of SN2 mechanism. And when it comes to SN1, substitution nucleophilic unimolecular. So in this case, what is the difference? The remaining comparisons I'll come back. We are just understanding once again what is it. So here it is unimolecular, so that from the name what all aspects come in. So unimolecular means
depends upon only that RS.
Yes, so we are having here the rate depending only on the substrate. It depends only on the substrate. So we are having rate of the reaction is equal to the rate constant into that of the substrate. Nucleophile is not a part of the rate determining step. So the rate determining step does not involve the nucleophile here. So during the course of the reaction, we are having, suppose I have CH3 thrice CCl as my substrate. So what happens initially?
Carbocation formation.
The carbocation formation. The Cl leaves out first. The Cl leaves out and we are getting the sp2 hybridized planar carbocation is formed during the course of the reaction. That's the rate determining step. It does not involve the nucleophile. So that is why it is 1. The name SN1, 1 stands for the what is involved here. It's only, but the number of steps, it's easy, whenever it's 1, the child you can tell. So here this is called as, so what is formed here is called as, so first step is shown here. X is leaving, X is the leaving group here. X moves out as X minus, and we are having R1, R2, R3 as the groups there, and carbon coming in. So carbocation is formed. So this is called as, therefore here we have a, in this case, the first step gives out a
Nucleophile, ma'am.
No, sir. What is formed?
Negative.
Carbocation.
We are getting an intermediate carbocation, is it not?
Yes,
We have a carbocation formation here. So that's very important because the rate or which is more faster, which mechanism is followed, all depends on all these. So the intermediate is formed here. Intermediate carbocation is formed here. And the intermediate carbocation formed is a planar molecule. Now when the nucleophile, so second step, the first step is where you having the nucleophile attacking. So when the nucleophile attacks, what is the possibility? So
Both
since
side,
it's a planar molecule, you can have, yes.
Both side nucleophile can attack by nucleophile.
Inversion.
Yes. So if it is attacking from the same side where you had X, what will happen?
A retention.
Yes. If it had attacked on the same side, it will be retention. Nucleophile attacking on the same side. Here we had the X here. Now the nucleophile is on the same side. So that's leading to retention. Same configuration. So we call it as retention. Whereas if it is coming from the back side, now the attack is from the opposite side.
Inversion.
So here you have the nucleophile on the opposite side. So inversion. So we have both inversion and retention of configuration happening in the case of an SN1 mechanism on a optically active compound. Is it not? When all the groups are different, you can have these two, and always this leads to, what about the product? So we it is always 50% of inverted
Racemic
product
mixture.
and 50% of
Racemic
retention.
DL mixture.
So, and this mixture is therefore, what about the
Racemic
optical
mixture.
activity?
It is
Yes,
optically
zero.
inactive. Zero.
Optical
Optically inactive.
Optically inactive. And what do we call this mixture?
Racemic mixture, ma'am.
Yes.
Yes,
This
yes.
is what we call as a racemic mixture. The process is racemization. We are having 50% of inversion compound and 50% of retention activity, and hence it cancels out, and the resultant mixture will be optically inactive, and we call it as racemic mixture. So always when we have an SN1 mechanism happening in an optically active compound, the resultant compound will be a 50-50% of inverted and retented configuration, and therefore it's a racemic mixture. No optical activity coming.
One more point, ma'am, because the tertiary alkyl halides only involved in SN1 mechanism, ma'am. That's why always optically active.
Tertiary carbon.
Tertiary, yes.
Stabilization.
Yeah, so that's what we are going to compare next. We are going to compare between SN1 and SN2 reaction. So now we've seen SN2 is a one-step process involving both substrate and nucleophile in the rate determining step, whereas SN1 is involving only the substrate. So it's a two-step process. We've got points of difference here now as being told now. So what type of substrates will undergo SN2 easily? What type of compounds will undergo SN2 easily?
Primary.
Alkyl halides.
Yes.
Primary, is it not? So why do we say primary? Why is it so that primary is undergoing more easily? Why primary? So SN1 mechanism, SN2 mechanism. SN2 is primary more easy compared to secondary, compared to tertiary. Now I have this mechanism also once. See, teachers, bromine leaving, water molecule attacking, and then a proton moving out. So this is how is the mechanism, is it not? CH3 tries a tertiary bromo compound. The first step will be the moving out of this, and therefore we are getting CH3
Proton.
cation is formed. Then we are having water molecule attacking on it through its lone pair. So we are getting CH3 thrice COH2. This is formed, and then one proton is eliminated. So you get the alcohol. So a good video showing this mechanism. A child can understand very clearly. Water, the solvent coming and attacking, then this H moves out. The lone pair coming onto oxygen, and oxygen getting back its lone pair, and thereby forming the alcohol. So this way, SN1 mechanism clearly displayed here. Another picture. So a lot of videos. Let's not waste time. We know students are the ones. So here, these are the points, isn't it? SN2 and SN1. So we had already discussed about being unimolecular depends only on the substrate, whereas both on the substrate and nucleophile, two-step and one-step reaction. Now we were discussing about this point. SN2 is favored by primary. A methyl group, isn't it? CH4. If I have CH3X, this will undergo SN2 mechanism very readily. What is the reason for that?
Because the steric hindrance, steric effect is not there, ma'am.
Right.
Because only the hydrogen atoms are attached to the center carbon. That's why there is no steric effect problem. That's why the attacking nucleophile can attack the during the presence of the leaving group also, ma'am.
Yes.
That's why this follows the SN2 mechanism, ma'am. But
Yes.
in SN1 mechanism, the bulky groups are attached, ma'am.
Yes.
That's why the attacking nucleophile cannot move towards the center carbon atom, ma'am.
Yes.
That may be the reason, ma'am. Thank you.
Yes, sir. Very right, sir. That's what. So this is how when we teach the children, is it not? The main aspect here is because the nucleophile has to attack at the same time as the halo group is leaving. So always it should be less sterically hindered. There should be no blocking. If something is blocking, then attacking that becomes difficult. So if you have less block, it will easily come and attach. So a methyl group containing a methyl halide will undergo SN2 mechanism very easily, followed by a primary, secondary, tertiary. Whereas when it comes to SN1 mechanism, it is through a carbocation intermediate, and hence we have taught the children tertiary carbocations are more stable compared to secondary or primary. So based on the stability of that intermediate form, the tertiary, whichever can form tertiary carbocation, that will undergo nucleophilic substitution by SN1 mechanism. So tertiary alkyl halides will prefer SN1 mechanism over SN2. What about a secondary alkyl halide? Secondary alkyl halides, if we look at
On a small dose, madam.
So there are a lot of factors. So one is the nature of the substrate. So, yes, sir, you were telling something.
Madam, methyl chloride is also, madam, methyl chloride also primary alkyl halide only, no, madam?
Methyl chloride.
Actually, order
Yes,
is first.
yes. Methyl, we
Halogen is
just say
attached to
separately, that's all.
That's all. It is not a primary alkyl halide. Am I right?
We call it separately as methyl because primary we say CH2 and an alkyl group. That way we say. Tertiary is C connected to all other carbons. Secondary, C connected to 2 carbons, 1 hydrogen. That way. Methyl also comes under, but we also sometimes specifically say methyl group containing. That's all. So this one, so
Methyl chloride also we can consider as a primary, madam.
Yes. So here no intermediate. So nature of substrate is one factor. What is the other one? Nucleophile, does it play a role? The nature of the nucleophile, does it play a role in identifying SN1, SN2 or going on for elimination?
It
So which
must be
can
strong
undergo even
leading.
elimination?
Yes, madam. It must be very strong electrophile. Nucleophile.
Nucleophile. Nucleophile should not be bulky, right? That's what you're saying, sir.
And
Heavy.
one more thing, it must be very easy leading group. If it is that order will be iodide is greater than, bromide is greater than, chloride
Leading
is greater
group.
than. Yes, madam. So leading,
Okay. So leaving group, what is going to leave? We are talking about haloalkanes, the nature of the halogen attached to alkyl halide, then the nucleophile. The nature of the nucleophile plays a role. Another important part is played by solvent. Solvent plays a very important role also in determining the nature or what type of solvent. So when we talk about, we've already seen substrate, and as just sir was saying, leaving group. So it's a halo group that is in haloalkane. So if we usually talk about reactions of chlorine, bromine and iodo compounds. So which type of compounds, is it a chloro, bromo or iodo, which undergo substitution more easily? Iodo. Why does iodo undergo more easily? Why is iodo a better leaving group?
Size is more, it can easily leave from that. So we can, nuclear substitution will occur easily.
Right. The size of the group, isn't it? Iodo is a bigger group, so bond length is more, bond strength is less. So it can easily break and move out. So if it's an iodo compound, always reaction, irrespective of whether it's SN1 or SN2, iodo compounds will be reacting faster. In both the cases, iodo group will react faster, followed by bromo and this. Now coming on to solvents. The nature of the solvent. In the case of SN2 reactions, the solvent used is a polar aprotic solvent, whereas in SN1, it is a polar protic solvent. I've given some examples also. Polar protic solvent. So water is a best example of a polar protic solvent. What is the need of having a polar protic solvent in SN1 mechanism? What is the need? So when I talk about RX in water, will it react to form alcohol? RX in water, can it form an alcohol? A tertiary haloalkane plus H2O. Aqueous medium. Polar protic solvent. So polar and protic. Any teachers? What will be the role? Why do we need to use polar protic solvent here? While in SN2, it's a polar aprotic solvent. So protic means, polar means what?
Polar means
It's
the solvent
polar. We
molecules
teach, no? We tell the children all the time, polar solvents.
break into positive and negative ion, ma'am. Just
Ions
like
can be
water.
produced.
Water.
Yes, sir.
Protein means
Yes.
proto
And
means
protic.
they can produce H plus ions, ma'am.
H plus, yeah, they can give H plus to an extent. Yes, right. So the role of a polar protic solvent in an SN1 mechanism. SN1 is a two-step mechanism where the nucleophile, the existing group has to leave, is it not? Suppose I have CH3, suppose I have this chlorine here. This chlorine has to leave. The chlorine has to leave. So how can that be possible? So there was a slide here. Yeah, this one here, a polar protic solvent. So it's mentioning here about the nature of the solvent and all that. And I have a table down here showing solvent and dielectric constant and relative rate. So we can see this dielectric constant of water is 78. Usually we say around 80. So what does that help in? What is the dielectric, high dielectric constant means? What is the role of water as a solvent? It has a very high dielectric constant. It's a universal solvent. What is its role? We have three solvents here, water, methanol, and ethanoic acid given, where you have one like 50,000, 4 and 1 is the rate of reaction when used as a solvent. So what does it imply, teachers? High dielectric constant means, how does it help?
They can produce H plus ion easily, ma'am.
Yes.
Easily split into plus and minus ions.
Yes. So water as a solvent will help in ionizing the species to a larger extent. So very large extent. And hence, so when we have this tertiary compounds undergoing SN1 mechanism, they have to split into carbocation and the X minus has to leave. So this is allowed by the solvent here. Water, when used, a high dielectric constant will help to split into the two species, and also it's a protic solvent. So how does that help? Protic solvent.
That H plus will easily take up that Cl minus.
Yeah, and also relates to hydrogen bonding also, is it not? It is capable of hydrogen bonding. It can enclose the halide ion there, not allowing, and the nucleophile can be easily, the nucleophile can move out and easily attack. Anything else adding, Lakshmi? Would you like to add something?
I think you've covered all the points.
Right. So this is, okay, thank you. So this is it. So polar protic solvent is a very important aspect in SN1 mechanism. We need a polar protic solvent for the reaction to happen. So that is why even if you take water, you take ethanol, the example that I showed you there, water coming and attacking, and then a proton being removed. So that is happening when you have a SN1 mechanism. It nature of the nucleophile that we require in SN, you can see, what is it? A weak nucleophile. Water is a weak nucleophile. That is enough to attack the species there because it is forming a carbocation intermediate and then attacking. Whereas when it comes to an SN2 mechanism, very important that we need a strong nucleophile, say like sodium hydroxide, potassium hydroxide, aqueous sodium hydroxide, potassium hydroxide, C2H5ONA, all these C2H5ONA. Ethoxides, all these are strong nucleophiles. So a very strong nucleophile and high concentration is required for an SN2 mechanism. So these are the main points when we come to the differentiation of SN1 and SN2 mechanism. I just have this question. Could you all just try out the first set here? Could you just rate them, which will be in increasing order of SN1 mechanism, or say decreasing, right? The decreasing order of SN1 reactions for these species. I have this moving.
Benzyl carbocation.
Get a carbocation here. this moving, we are getting this. Yeah, ma'am.
Yes, ma'am.
So this is a benzylic and this is a tertiary carbocation. Here, stability when you look in, secondary, yes. This is an allylic carbocation.
Yes, ma'am.
And in this case, it's a normal secondary carbocation. So B and C, do you say B and C? You told me B is higher, C is next. Do all agree?
C will be most reactive.
Yes.
Then comes your A. Then D.
After
Then
C,
B. After C, it will be A.
will it be tertiary is here, Lakshmi?
Yeah,
What do you think? Not
yeah,
tertiary.
tertiary.
This is just
hyperconjugation.
benzylic.
Yeah. So it will be
Compared to
C,
that, no?
yeah,
B should
C,
come, no?
D, yeah.
After 1, 2, then it will be A, no?
Yes. Yes.
This one,
Then it will be D.
allylic, yes.
And then C. E.
Yeah. This should be right. Yes. Teachers, do you agree? Because here, though it is tertiary, in this case, we have this benzene ring stabilizing as well as the methyl group stabilizing. So when such a case comes, this will be more stable, even though it's a tertiary there. So after this, then comes your benzylic one, then comes tertiary, then comes benzyl carbocation. And here D is stable because of the resonance due to the allylic species. And then lastly will be a normal secondary carbocation. Yes, teachers?
Yes, ma'am. Yes, ma'am.
Right.
Also
And the
plays
other
a
one
role.
I've given is just simple. So that's very easy, right? First one
Yes,
is
ma'am.
more complicated. So here,
Tertiary.
tertiary, secondary, primary is what we are getting.
Yes.
And primary. So anyway, the order is as given here.
Yes.
Right. So these type when it comes in, slightly coming in. And all the examples of a few strong nucleophiles, we have the alkoxide ions that come in alkoxide. Then alcoholic AOH will provide ethoxide ion, sodamide, tertiary butoxide. All these are very strong nucleophiles like water, alcohol, phenol, which act as solvent also will be behaving as weak nucleophiles. There you don't need an extra reagent there to produce a nucleophile. So for SN1 mechanisms, weak nucleophiles are enough, whereas for SN, two mechanisms, strong nucleophiles are required to attack because they attack at the same time. And this is another aspect about the nucleophile coming in. So what type of nucleophile, strength of nucleophiles? An anion is a stronger nucleophile than a neutral molecule. And if we look at a group, nucleophilicity is inversely, it's directly proportional to the size of atoms. So if I look at chlorine, bromine, iodine and all that, iodine will be a better nucleophile than chlorine. Though here we are going to discuss about them leaving. And if you look at a period, if you're comparing species belonging to the same period, then a better nucleophile will be the one which is having lesser electronegativity. And a better nucleophile will be less stable because a less stable species will not go and attack. It's already stable there. So with this in mind, can you tell me among these two, OH minus and H2O, we had already discussed, which is a stronger nucleophile?
H2O.
OH minus. No, we talk anion is a stronger nucleophile than a neutral molecule. And alkoxide ion and alcohol. Alkoxide ion, yes. So that's why we saw the previous example also. Alkoxide ion is a stronger nucleophile. Now, if you compare water and H2S, if you look in, which will be a better nucleophile?
H2S.
H2S, because we have this third a group. In a group, nucleophilicity is directly proportional to size of atoms. So oxygen and sulfur down the group, sulfur larger. So H2S is a better nucleophile. And I just discussed about iodine, bromine. So that can be compared in a group. So group nucleophilicity proportional to size of atom. So again, I minus will be a stronger nucleophile. What about NH2 minus and PH2 minus?
Nitrogen.
NH2 minus and pH 2 minus. So we are comparing species belonging to the same group. So group, we have to see the size. Larger the size, better is its nucleophile nature.
pH2
Yes,
minus.
pH 2 minus. Yes, ma'am, right. And the next set there we have SH minus and H2S.
SH minus.
SH. So first two, no doubt, because it's the anion versus
Anion.
neutral molecule. So SH minus and phenoxide ion. When it comes to fluoride, hydroxide, and NH2 minus, what will be the order?
F.
I
First
minus.
one is F minus, ma'am.
F minus. So they are belonging fluorine, oxygen, nitrogen, belonging to the same period.
Period.
So there it is inversely proportional to electronegativity. More electronegative will be less, will act less as a nucleophile. So which will be the order? Which will be the order? Fluorine, oxygen, nitrogen, what is written is in either increasing, decreasing order. So
Increasing order.
fluoride will be a
Lesser.
lesser. This will be more.
Yes.
And
yes.
coming on to CH3, CH2O minus and C6OH, C6H5O minus. That relates to the last point here.
Inverse, the 1 by stability.
Inversely proportional to stability. So if it is more stable, it is not.
CH2, CH3, CH2O minus.
First one, ma'am.
First one.
Will be a better, because aromatic compounds are stable,
Resonance.
is it not? They are stable by resonance. So this will be a better nucleophile because this is a stable species. It will not tend to move and attack. It's stable by itself. And what about these two that I've given? Though we don't use all this here, but just I thought. In these two, how do we compare?
First one, second one is more electronegative, I think, ma'am. Because more resonance possible in first one, I think, ma'am.
Okay, sir, resonance possible. Can we talk in terms of aromaticity?
The second one is an anti-aromatic compound.
Yeah, and this is
First one is
aromatic, right?
Aromatic, so stable.
Second one is
First
aromatic.
one is aromatics. So this is
No.
stable. No? 4n
Yes.
plus 2 rule.
Yes, ma'am.
This will satisfy. So this will be aromatic stable. So then that means this will be a better nucleophile. Just thought we will just go a little deeper into it. That's all. Though we are not using any of such nucleophiles for reacting with the haloalkane, we go in only for all these species, hydroxide, alkoxide and all that. But still, so these are the few informations about the nucleophile. How can we identify whether it's a strong nucleophile and all that? What about the rate of SN2 reaction in a few? SN1 is the first set here. The first comparison here between these two.
First one is less than second one.
Yes, because this will be forming a tertiary, right? So this will be faster in the SN1 mechanism. What about the second set, teachers? Leaving group is the same in the examples 1 and 2.
Yes.
So which here we have to immediately think about the carbocation that is being formed. So
First is more reactive than the second.
first is more reactive than the second, yes. Based on?
Allylic
Allylic
carbocation.
Yes,
and
allylic
vinylic
carbocation, is it not? Allylic stability of the carbocation form, this will be. And in the third case is only comparison of the
leaving.
leaving group.
Leaving group.
Be it SN1 or SN2, it's only the leaving group. So this will leave faster and form a carbocation. So this will be the order. So this is not very much here. What about the SN2 coming in here? SN2. In the first set,
Yes. First one is less than second
which
one.
one will easily undergo SN2?
First one is better than second one.
First one faster than second one. Why, sir? Why do you think so?
Because that ethyl group, one more methylene group is donating electron, the sigma bonded electron towards the chlorine. So that is the reason it will not be. It is less stable, madam, compared to first one.
This is less stable. So here we are talking about SN2 mechanism. SN2 mechanism. So we are looking in for steric hindrance, right?
Yes, madam.
So in that case, do you say first one?
First one is better than.
First one is greater. Do you all agree, teachers?
Actually,
Teachers,
first one
is it
goes for
other teachers?
SN1. The first
Which
one
one?
will go for SN1.
Second one goes
Second
for?
one goes for SN2.
2.
Yes,
So first
SN2, right?
Then second one.
Yeah, because this one will prefer SN1.
Benzylic carbocation.
Yeah, here comparatively it's HH and this comes, whereas here this is directly, the aromatic ring is directly attached to this carbon. So there is steric hindrance. So this will not prefer SN2, whereas here this aromatic ring is attached to the next carbon. So the steric hindrance compared to this is less. So when asked to compare for SN2, this one will be favoring SN2, right?
Yes.
Less, because SN2 is ours, we can say less steric hindrance. Yes?
Yes, ma'am.
As this group leaves, it can attack because the benzene ring is not directly attached to that carbon. And now coming on to this one is a very easy example.
Yes, ma'am. Tertiary, secondary,
So
primary.
this is specifically tertiary, secondary, and primary. So our reactivity order will be
Decreasing.
is it which one undergoes SN2 faster?
First, this one, last one.
Last one. So I have to put it in this way, right?
Yes, ma'am.
The last one will be more reactive towards SN2 mechanism. And the last one example is the same. Only thing is comparison of the leaving group. So that when we put the point of difference, I had put both good leaving groups, same point, same. There's no difference in that aspect. It's only
Because of
based on the nature of your substrate, tertiary, secondary, solvent aspect and all that comes in here. So, and when it comes to tertiary compounds, tertiary alkyl groups, there is also a possibility of elimination coming in, is it not? So when do they go in for elimination? When do they go in for substitution? Tertiary compounds. Class 12 level, that is what we are teaching the children. EBA and E2 mechanism we are not going into. We are just talking about comparison of some tertiary compounds may undergo elimination, but under what condition? So when we are using aqueous KOH, when we are using alcoholic KOH reacting, what is the difference? If I have CH3 thrice Cl undergoing reaction with aqueous KOH and with alcoholic KOH. CH3 reacting with aqueous KOH and alcoholic KOH. What difference does it make, the solvent?
Alcoholic KOH means beta elimination method.
Yes.
And that alkene will be formed.
Yes, right. So in the case of alcoholic KOH, it prefers elimination. Whereas aqueous KOH goes for
Alcohol.
alcohol. This is one important thing we tell the children, right? The use of a different alcoholic KOH results in elimination. It will result in abstracting a proton rather than going and attacking and substituting. It will take up a proton, go in, and then form KCl and H towards the products there. So base solvent will play a role here. So class 12 level, this is only enough. We don't go in for any other mechanism part and all that. So those are the basic things related to SN1, SN2 there. Teachers, anything else that we have to go into there?
Ma'am, actually, what is the reason why aqueous KOH gives alcohol and alcohol prefer beta elimination? Is there any particular
Alcoholic
reason?
KOH solvent. So here, it will result in abstracting a proton, ma'am. It takes out CH3. It will, rather than moving in there, it will be abstracting a proton from here and then resulting in the compound formation.
Okay.
Any other thing?
Also, the alkoxide is a better base.
Alkoxide, yes. C2H5OH and KOH results in C2H5O minus. So this will abstract a proton. It's a stronger base. It will act as a stronger base than acting as a nucleophile. The role of a base is to abstract the proton there. It will be taking out a proton. C2H5O minus will take out a proton and then result in the formation of alkene.
Yes, ma'am. Thank you.
Right, ma'am? Yeah, this
Yes,
is the
ma'am.
important part. Yes. I thought we'll just discuss this two slightly different. What do we give this as a, what product here? What process goes in? Mechanism?
Free radical. Free radical.
Yes, sir. So what will be the product?
CH2Cl. Br. CH2Br.
CH2
Br.
Br CH3, right?
Yes.
CHBr CH3. CHBr CH3. Why do we give this as the product? How do we, how does the child understand here? Yes? Why not CH2 CH2Br? Why is it CHBr CH3?
Two possibilities. CH2 CH2Br and CHBr CH3. Two possibilities.
Possible, but mainly we give them, the major product can be because it's forming a, if it's CH3 terminal hydrogen which goes, it forms a primary free radical. If this moves out, it's forming a secondary carbon free radical. So this being stable, this is the product, right? Yes, teachers?
Yes, yes.
And what about the sixth one here? What will be the main product?
Vicinal dihalides.
Is it vicinal dihalide?
No, actually, the
Condition is heat, high temperature.
yes, madam. Here also free radical.
Free radical.
Yeah, so what do we get?
Dibromo.
No, ma'am, not dibromo here.
Madam, one bromo cyclohextuene.
1-bromocyclohextuene. So we are saying allylic, right?
Yes, madam. Allylic.
Do we call it as 1-bromo?
Bromo.
It cannot be 1-bromo, right?
Yes, madam. 3-bromo, madam. 3-bromo cyclohextuene.
So what is the, why is it so? So you're getting allylic halogenation.
Yes.
So if the temperature, when temperature goes in higher temperatures and all, it prefers allylic halogenation. This is one thing which is slightly different here. Allylic halogenation happening in presence of heat, UV light. So this thing has to be going in high temperatures rather than going in for addition, double bond breaking. It prefers substitution because addition reactions are reversible at high temperatures. So it prefers going in for substitution at high temperature. This one is a slightly different question compared to the others. And all these comparisons is not arranging in order based on isomeric haloalkanes. So based on the surface area and therefore intermolecular. All this is clear now, teachers. We need not discuss these, right?
Yes, ma'am. Yes, ma'am.
Boiling point, and here specifically this melting point part we have to only this
Yes,
one
ma'am.
melting point difference
Yes,
is
ma'am.
mentioned. Boiling point is similar. So the reason for the higher melting point of this para isomer is often asked question. Density is fine, solubility also. The solubility now haloalkanes here. So finally, after fully or all the organic taken, we'll be comparing between haloalkanes, aldehydes, all this. So this physical property comparison is very important coming in there. So we had discussed about the nucleophilic substitution. Coming on to questions of this type, very important comparison.
Yes.
There was one molecule here which I wanted. Yeah, this one. This one, what happens in this reaction? -2 methyl butane 1 all reacting with HCl, concentrated HCl. So here, during the reaction, is that an asymmetric center where the bond is breaking? Is it an asymmetric compound? Is it chiral? Is the
No.
molecule chiral?
No, ma'am.
See, ma'am, molecules chirality. H here,
Yes, yes.
methyl group here, methyl group here,
Methyl
and
group here.
CH2OH here. So this particular carbon
Hmm.
is chiral, right? It's an asymmetric
Yes, yes,
center.
yes, yes. Yes,
But-
artically active. Hmm.
Now the reaction happening, HCl, chlorine substituting for oxygen. Is that breaking the asymmetric carbon bond?
No.
No. So this reaction does not involve the breaking of the asymmetric carbon bond.
Carbon.
It's the other one coming in here. Okay, so there's one particular example mentioned here, but it is seen that its optical activity is different. So that's based on the compound. Different compounds with same configuration at asymmetric center can have different optical rotation. So this one mentioned here, not
Yes,
based
ma'am.
on the asymmetric center. So that one was mentioned.
Hmm.
And examples particularly given, all this is fine. So elimination versus substitution reasons they have given, which route takes based on whether the nucleophile is bulkier. And as told here, you can see the alkoxide ion. So what comes, how it reacts and all that. The reaction with metal we had just seen. This is another important reasoning question which is always asked. Why is it necessary to keep it free from moisture? Grignard reagent should always be stored free from moisture.
Yes.
Is it not?
Hmm.
A very often asked reasoning question. Most board exams you have seen this type of question being asked. So what do we give as an answer there? And it can also be used as an important
Hydrocarbon.
reaction.
They will
You can
easily
convert a haloalkane to RX,
hydrocarbon.
can be converted to a hydrocarbon through this. Corresponding alkane can be obtained if you use water or if you use ethanol, anything which can give which can protonate the Grignard reagent, so that which can react there. So that will be converting. So this is one important, this part. Okay.
Yes, ma'am.
So what's now another important aspect is why do aromatic haloarenes not undergo nucleophilic substitution reaction? And we have 4 points they mentioned. So this one always we talk about resonance. The other 2
Partial
points are
Partial double bond
I mean,
character.
3 points, yeah. Partial double bond character due to the sp2 carbon here, the partial double bond character. So the bond is stronger, difficult to break. What about the third point? If it loses the X, it is going to form?
Carbocation.
Phenyl carbocation.
Loses this, now it forms phenyl carbocation. And phenyl carbocation stability?
Stability more.
Will it be stable? Phenyl carbocation?
No.
It is not stable, is it not? There's no possibility of resonance. You have a double bond here. There's no possibility of resonance coming in here. So instability of the phenyl cation that is formed. And lastly, so nucleophile is what type of species? It's an electron-rich species. And your aromatic benzene ring is also electron rich. So they will be phasing, they'll suffer repulsion. So these are the additional points which we explain to the children as to why they do not undergo nucleophilic substitution reaction. Haloalkanes easily undergo nucleophilic substitution reactions while haloarenes do not undergo. So apart from these two main points, these two also hold good. These 2 points coming in.
Yes.
Caustic conditions under which you can convert haloarene, chlorobenzene to phenol, while chloromethane can be easily converted to methanol. It is so difficult to convert this. And also the role of
Electron withdrawing group or
electron withdrawing groups present in ortho and para position, how they decrease the electron density, thereby making the the substitution more easy, nucleophilic substitution. We do give them an indication of all this, but exam point of view, not very much important. And the other in-text question there, this one. Although chlorine is an electron withdrawing group, yet it is ortho-para directing in electrophilic aromatic substitution reactions. Why? So this is one thing, no, where the child, why this is happening, why is it so? So what are the 2 aspects we go in there?
chlorine.
Chlorobenzenes, nature, chlorine is close. Electron withdrawing inductive effect, and at the same time, due to the presence of lone pairs, it can also show the resonance effect coming in. So what favors what? Deactivation is due to what? It is deactivating, and at the same time it is ortho-para directing. Ortho-para directing. So what favors what? Why is it deactivating? Is it due to -I or D plus R effect? Deactivating?
-I.
Due to the -I effect, how does it become deactivating? Yes. So clearly mentioned here. So when it forms the carbocation here, so what happens to that? Because it pulls out the electrons, it withdraws the electrons away. It will destabilize the carbocation, is it not? The positive charge is all the more increasing. Yes, teacher?
Yes, ma'am.
Yes. Inductive effect, that is the reason it destabilizes the intermediate carbocation. So when it attacks here, this one becomes negative, positive. So you're having an intermediate carbocation formed, which one will be destabilized due to the electron withdrawing effect. And now, second factor, it's ortho-para directing. It's ortho-para directing. There, what do we say? So that's due to the
Resonance effect.
Plus R effect, is it not? Due to plus R effect, you have the electron density increasing at the ortho and para position. When we are showing the resonance, we know how ortho para positions becoming electron dense. So an electrophile can attack easily at these positions. This is another question which both contradicting. It is deactivating. I just thought we'll touch upon those type of questions which often comes for board and all that. And Woods, It's clear now, teachers. When it is a Fittig reaction, it is. So we have three types there: Woods, then we have Fittig, and we have Woods Fittig. So its reactions are similar. Sodium and ether reacting with halides. So what is the difference? Woods is for only
Same.
Open chain.
haloalkanes, right? Yeah. Haloalkanes. Whereas Fittig comes in when it is
Haloarine.
Haloarenes. We have an example here. The other day, Ganesh sir, you had put up a question, no sir? So that was clear, right? You had put up a question in the group about woods here giving diphenyl. Biphenyl is the same. The name is the same. It's the same compound. And when it comes to Woods Fittig, what is the difference?
Both alcohol and aryl halides.
Woods Fittig is when we have a combination of RX and haloarine reacting with sodium and dry ether. So we are going, what type of compound do we get when we go in for that? So if I go in for CH3Cl and C6H5Cl.
Toluene, ma'am.
So we get toluene, is it not? So this one. So one Na goes with the Cl, another Na. So in dry ether. So we're going to get CH3, C6H5. So when we need aryl compound, when we need aryl compounds, we can go for Woods Fittig reaction. Yes, so that's the only difference there. When the names are differing, the reaction is similar. And very often, these type of compounds are very often seen in the exam. Comparison SN1, SN2. Though very simple, but easily scoring if the child understands this part. Compounds. Last year it was deleted, but now we have this, so we can just go in for it. And any particular questions here that we need to discuss, children? Teachers, lot of conversions here, no? Question number 11 and question number 19 is full of conversions. And another one is this type of questions.
Arrangement, order.
Yes, ma'am. Conversions are all fine, ma'am. This is again like all the child will be able to do all complete conversions only after we teach all the chapters together. That's what usually happens. A few conversions we may not be able to touch upon. Yeah, that's what. And somewhere we had amines also, no? Where we use isocyanide and all that. Some question, I think phenyl isocyanide here.
Aniline to phenyl isocyanide.
Yeah, that's what. This question relates to that chapter. Anything here, teachers, which it's fine, right? Ethanol to but-1,9, we have to always go in back to class 11, right?
Alkyne.
Ethanol to but-1,9 conversion. Here when we look in, how do you all go about the conversion? Ethanol to but-1,9, same thing I think comes in here also. Yes. Yes, teachers? If you randomly just try to connect
Ethyne,
to
sodium ethanol.
refresh back the methods, conversion. Yes. No, we are going in for a step up. So ethanol to be converted to but-1,9. So whenever we go teach children conversion first, write the starting reactant, write the product. Yeah, so from this, how can we arrive at this? So can we convert alcohol? So first thing is it has 2 carbons here, whereas here it is 4 carbons. So there is some way that you have to increase the number of carbons here. So ethanol to but-1,9. So can we convert an alcohol directly to but-1,9? So what is the possibility? How do we convert? So how can I prepare an alkyne, a 4-carbon alkyne starting from a 2-carbon alcohol? Yes,
We can
teachers?
You can take more than 1 molecules of 1 mole of ethanol, ma'am.
Okay, sir.
By dehydration, we can, by elimination reaction, we can dehydrate, ma'am. Then the alkyne can produce, ma'am.
You prepare alkene only, no? So dehydration will result in ethene.
Oh, okay, ma'am. Now
No,
we want the
dehydration gives ethene.
Yes, ma'am.
So how do we go about? We need a 4-carbon alkyne. So Lakshmi ma'am had mentioned. So this first we have to convert to haloalkane, right? Any haloalkane, we can convert it to any haloalkane, say thionyl chloride. So we are converting it to haloalkane, chloroethane. From 2-carbon chloroethane, we have to convert to 4-carbon alkyne. So class 11, we would have taught the children about alkenides, right? Sodium alkenide. Yes, teachers? When a haloalkane reacts with sodium alkenide,
We would have compared the acidic character of ethane, ethene, and
yes.
ethine. So there we would have told that ethine is the most acidic substance because of
Right.
sp carbon.
CH is not sp carbon hydrogen attached to
Yeah.
an sp carbon.
It's
sp
most acidic.
this carbon being more electronegative compared to sp2 or sp carbon, the CH bond. So C is more polar. So H will be H is an acidic hydrogen. For a C triple bond H, highly acidic compared to CH2 double bond CH2. This hydrogen is less acidic because it's an sp2 carbon. And CH3, this is a sp3 carbon to which hydrogen is bonded. So less electronegative. So more electronegative sp, more acidic hydrogen. Acidic hydrogen is more acidic. So it can be easily replaced by sodium or sodamide. Anything, sodium can replace this. So this way we get alkenides. CH triple bond CNA. If there's excess of sodium, the other hydrogen can also be replaced. So this is what we are going to use here for the conversion. We can use sodium alkenide. So we have started with a 2-carbon compound and we need a 4-carbon alkyne. So what alkenide should we choose? Already 2 carbons are here. So we are going to take up. What can we use? Yes, teachers?
Sodium ethanide.
Yes, sodium ethanide can be used. So we are using sodium ethanide, and so it is going to react, and thereby NaCl is eliminated, and thereby do we get this product now? Is it this now?
Yes, ma'am.
CH3, CH2, C triple bond, CH. So whenever we need, say, alcohol, haloalkane going into a higher alkyne, so immediately connected to this nature, formation of sodium alkenide by alkynes, easy. That's what we use in S block also, one of the points of difference, anomaly between lithium and other compounds. We go in for alkenides, not forming alkenides and all that. So this one conversion here, slightly different coming in. Any other teachers which you all find a little difficult when you discuss with your students? Ethane to bromoethane has more number of steps coming in, but it's fine. Number of steps is more, that's all. Another one, bromomethane to propanol. We can connect it to chapters, aldehyde chapter. Bromomethane to propanol. I think it's almost time. Can we just stop, discuss this and stop off? Bromomethane to propanol.
Yeah.
Easy way when we connect it to the chapter of aldehydes that we have learned. Converting bromomethane. CH3Br is to be converted to propanol. So what is the possibility? 1 carbon haloalkane to be converted to a 3 carbon ketone. Again, it's a step up, but what possibility of converting it to ketone? How do you give, what method do you give, teachers? A simple 2-step can go in. If you just discuss, we can finish off. It's already 5:31. Anybody?
No, ma'am.
We can convert it to nitrile, ma'am. When we
Try to use it on, try to convert it into Grignard and treat it with ethanol.
ethanol, yes, right. That way, yeah, 2 ways we can go in. As told, yeah, we can convert it to Grignard, right? CH3, MgBr comes in, and then we can convert
Ethanol.
it to
Secondary
alcohol, right?
Yeah.
We can convert it to alcohol. So it should be giving a secondary alcohol. For a secondary alcohol, we have to choose. We already have 1 methyl group here. So we have to introduce 2 methyl. So we'll take up CH3, CH2. I mean, sorry, CH3, CHO, right? Ethanol
Mhm. Yeah.
followed by hydrolysis. So that will give you CH3, CHOH, CH3. And partial oxidation with CrO3 will give this. And also, can we go in through nitrile?
Mm.
We can go through nitrile, right?
Yeah.
If we treat with, say, potassium cyanide or sodium cyanide, this is converted to CH3CN. And this one, if we treat with Grignard reagent, CH3MgBr. Yes?
Yes.
So CH3, if I show all the steps, it'll be triple bond. It'll be NMgBr. And this will be CH3. And then hydrolysis, this will become double bond O. So that's one easy method related to the reactions that we learn in that chapter. So KCN, then this, or Grignard reagent. And then if you can go for nitrile here, also fine. Is this or nitrile you told, Lakshmi?
The first one with the red, what you have done, no?
Yeah, we can go through nitrile here, right?
Yeah, yeah.
This way, reverse. We can go this way rather than
Yeah.
going in 2 steps. So different possibilities. If this chapter, if they are thorough with the conversions, children, that means they are thorough with almost all reactions. Lot of reactions coming in here.